Hello, in this lecture we find out the area of a circle. In the drawing we have a circle and we have also triangle ACP. This is again ACP that is equals to 90 degrees inside, therefore triangle ACP is a right angle, and triangle ACP or side AC has the circle at 2 points, A and this point. We know that side CP of triangle, the right triangle ACP equals to 4 units in its length, CB equals to 1 unit in its length, and from this point, point P, we have two tangents to the circle, tangent PA and tangent PB, and our mission is to find out the area of the circle. So here we can implement first of all rule 2. Why? Because from the common point point P, we have two tangents to the circle, tangent PA and tangent PB, and according to rule 2 they are equal to each other. So please put on rule 2. According to rule 2, the lengths of two tangents from common point to a circle are equal. So in the drawing we have a circle, and this is the common point P. From this common point P, we have two tangents to the circle, tangent PA and tangent PB. According to this rule 2 they are equal to each other. That is to say, PA equals to PB. So we can implement rule 2 in our drawing. Because from common point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. So I write it down. If you focus on the common external point P, for the common external point P, we have two tangents to the circle, tangent PA and tangent PB, and according to rule 2 they are equal to each other. That is to say, PA equals to PB, according to rule 2. PA is the missing tangent, so we limit as it is, so PA equals to PB, and PB equals to PC plus CB. So PB equals to PC, that is 4, plus CB, that is 1. So in total, PB equals to 1 plus 4, that is 5. So PA equals to PB, that is equals to 5. And from the equation PA equals to PB equals to 5, we will derive that PA is also equals to 5 units in its length. PA equals to 5. So here, PA equals to 5 units in its length. The next step, we'll focus on the right triangle ACP, and we'll implement the Pythagoras theorem on this right triangle ACP. So I'll copy the right triangle ACP in the new page and we'll implement the Pythagoras theorem on the right triangle ACP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a relation for Pythagoras theorem. So actually, this is the right triangle ACP, that is according to the original drawing, according to the Pythagoras theorem, in this right triangle ACP, AC squared, that is the square of the AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. So I'll write it down. AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. AP is 5, therefore AP squared is 5 squared, that is 25. And it is equals to AC squared. AC is the missing side, so we leave it as it is. So it is AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total we found out that 25 equals to AC squared plus 16. Here we subtract 16 from this equation, and finally we get that AC squared equals to 25 minus 16 is 9. So AC squared equals to 9. Here we take a root out of this equation. Finally, we get that AC equals to the square root of 9, that is 3. So AC equals to 3 in its length. So here AC equals to 3 in its length. We know that angle ACP equals to 90 degrees in its size. And we know that also that PB is a straight line. So on the upper side of the straight line PB, this is angle ACP that is equal to 90 degrees in its size. And according to rule 3, the sum of the angles on one side of the straight line is equal to 180 degrees. So if we focus on the upper side of the straight line PB at point C, here the sum of the angles must be equal to 90 degrees in its size. So which angles we have at the upper side of PB, of the straight line PB at point C? We have this angle that is 90 degrees, plus the missing angle. In total, the sum of those two angles must be equal to 280 degrees, according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will define the center of this circle. This point is point O. We join points O and B together by straight line. Point O is the center of the circle, point B is the point of the circle itself, therefore OB is the radius of the circle. We define the radius of this circle as x. So OB equals to x. Here we can implement rule 1. I think we can rule 1. According to rule 1, the tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we have also tangent AB, this is tangent to this circle at point M. Point M is the point of tendency of tangent AB with this circle. And we also have the radius OM that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Well, because in our drawing, we have the radius OB that is equal to x. The radius OB is on to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees. According to rule 1, of course. So in the next step, we will join points O and A together by straight line. OA is of course the radius of this circle that is equal to x according to our definition. In the next step we will do a construction, that is to say from the center of this circle, that is to say from point O, we will draw perpendicular on AC. Again from point O we will draw perpendicular on AC. So actually this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point N. So by doing this construction, we created here quadrilateral ONCB. Inside quadrilateral ONCB we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 pieces angle must be equal to 90 degrees in its size. In order to complete the sum of the angles inside quadrilateral ONCB to 360 degrees, the missing fourth angle, this missing fourth angle must be equal to 90 degrees in its size. So inside quadrilateral ONCB we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this right angle if not a square. So we relate quadrilateral ONCB is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ONCB, side BC must be equal to the opposite side ON. But to the opposite side ON. But BC is 1, therefore the opposite side ON must be also equal to 1 unit in its length. Likewise, according to the same rule, in the same rectangle ONCB, side OB must be equal to the opposite side CN. But OB is x, therefore CN must be also equal to x units in its length. We already found out that side AC of the right triangle ACP equals to 3 units in its length. Therefore AN, what is the length of side AN or line segment AN? AN must be equal to AC minus NC. Again, AN equals to AC minus NC. So I write it down. AN equals to AC minus NC. So AN equals to AC. AC is 3 minus NC. NC is x. So in total, AN equals to 3 minus x units in its length. So in the next step, we will implement the Pythagoras theorem on the right small triangle, triangle AON. So I copy the right small green triangle AON in a new page, and we will implement the Pythagoras theorem on this small right green triangle, triangle AON. Here by PT is a version for Pythagoras theorem. So actually, this is the right green triangle, triangle AON that I go to the original drawing according to the Pythagoras theorem. In this right triangle AON, AO square, that is the square of the hypotenuse, equals to AN square plus NO square. So I write it down. AO square, that is the square of the hypotenuse, equals to an squared plus on squared. AO is x, therefore AO squared is x squared, and it is equal to an squared. An is 3 minus x, therefore an squared is 3 minus x squared plus on squared. On is 1, therefore on squared is 1 squared, that is 1. So in total we found out that x squared equals to 3 minus x squared plus 1. So here we'll open the brackets on this side of the equation, and we get that x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared, minus 2 times 3 times x is minus 6x, plus 1. So here we have x squared on both sides of the equation, so x squared will get cancelled. After cancelled x squared, in the side of the equation we have to nothing, that is to say 0. On the other side of the equation we have 9 plus 1 is 10, minus 6x. So if we found out that 0 equals to 10 minus 6x, here we add 6x to this equation, and we get that 6x equals to 10. So I found out that 6x equals to 10. Here we divide this equation by 6, and finally we get that x equals to 10 over 6. So here we divide both the numerator and the denominator of 10 over 6 by 2. So x equals to 10 over 2 is 5, and 6 over 2 is 3. So in total we found out that the radius x of this circle equals to 5 over 3 units in its length. So what is the area of the circle? The area of any circle equals to pi times the radius of the circle squared. So the area of the circle, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of the circle will be equal to pi, and the radius is x, that is 5 over 3. So the radius squared is 5 over 3 squared. So if we found out that the area of the circle equals to pi times 5 over 3 squared. 5 over 3 squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total we found out that the area of this circle equals to either 25 pi over 9 square root, so in terms of numbers it is equals to 8.727 square units. And that is the answer to the question. Okay, again, if we found out that the area of this circle equals to either 25 pi over 9 square root, so in terms of numbers the area of this circle equals to 8.727 square units. So in the next step I'll summarize the lecture. So in this lecture our mission is to find out the area of this circle. So in the drawing we have a circle, and we have also the right triangle ACP that cuts the circle at 2 points, point A and this point. We know that this is angle ACP, that is the right angle. CP equals to 4 units in its length, BC equals to 1 unit in its length, and our mission is to find out the area of this circle. So first of all, if you focus on this common external point P, from this common external point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. So okay, again, rule 2, according to rule 2, the left of two tangents from a common external point to a circle are equal. So So in the point we have circle, and this is the common external point, point P. From this common external point, point P, we have two tangents to the second. Tangent PA and tangent PB. And according to this rule, all two they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. One put in our drawing, we have the common external point, point P. From the common external point, point P, we have two tangents to the second, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. According to rule 2, if you focus on the common external point, point P, tangent PA equals to tangent PB. So PA equals to PB. PA is the missing side, and it is equals to PB. We know that PB in total equals to PC plus CB. That is to say, PB in total equals to PC, that is 4, plus CB, that is 1. So in total, PB equals to 4 plus 1, that is 5. So here, PB equals to 5 units in its length. And from this equation, PA equals to PB equals to 5. We derive that PA also equals to 5 units in its length. So this is side PA, that is equal to 5 units in its length. In the next step, we implemented the Pythagoras theorem on this right triangle, triangle ACP. So copy triangle ACP in a new page, and we implemented the Pythagoras theorem on this right triangle, triangle ACP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right triangle ACP that is coming from the horizontal domain. According to the Pythagoras theorem, in this right triangle, triangle ACP, AP squared, that is the square of the hypotenuse, must be equal to AC squared plus CP squared. Again, AP squared equals to AC squared plus CP squared. AP is 5, therefore AP squared is 5 squared, that is 25, and it is equals to AC squared. AC is the missing side, so we limit the CT, so it is AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total we found out that 25 equals to AC squared plus 16. Here we subtract 16 from this equation and found out that AC squared equals to 25 minus 16, that is 9. So AC squared equals to 9. Here we took a root out of this equation and finally found out that AC equals to the square root of 9, that is 3. Okay, this is side AC, that is equals to 3 units in its length. So we actually found out that quadrilateral ONCB is rectangle, and you know that the opposite sides of rectangle are equal to each other. This is to say side OB equals to side NC, but OB is X, therefore NC is also X. Likewise, according to the same rule in the same rectangle ONBC, side BC equals to side ON, but ON is 1, but the BC is 1, therefore ON is also 1. So we know that NC equals to X units in its length, and AC equals to 3 units in its length. AN equals to AC minus NC. Again, AN equals to AC minus NC. Repeat again. AN equals to AC minus NC. So AN equals to AC, that is 3, minus NC, that is X. So in total, AN equals to 3 minus X. In the next step, I complete the right green triangle, triangle AON in a new page, and implemented the Pythagoras theorem on this green right triangle, triangle AON. Okay, this is the right green triangle, triangle AON. Actually, before that, we did here a construction, that is to say, from point O, we go perpendicular on AC. So this again equals to 90 degrees, and this again also equals to 90 degrees according to our construction. By doing this construction, we created here quadrilateral ONCB, and we found out, I already explained that quadrilateral ONCB is a rectangle. Okay? We know that the opposite sides of the rectangle are equal to each other. OB is X, therefore NC is also X. BC equals to the opposite side ON, in left angle ON BC. But BC is 1, therefore ON is also 1. And just like the formula that AN equals to 3 minus X units in its length. Here if we join points O and A together by same line, OA is the radius of the circle that is equal to X. So I copy the right triangle AON in an equation implemented the Pythagoras theorem on this right triangle AON. The right triangle AON. So okay, this is the right triangle AON that I copied from the original drawing. It's going into the Pythagoras theorem in the right triangle AON. AO square equals to AN square plus ON square. And AO square equals to AN square plus NO square. AO is X, therefore AO square is X square, and it is equal to AN square. AN is 3 minus X, therefore AN square is 3 minus X square plus ON square. ON is 1, therefore ON square is 1 square, that is 1. So in total we found out that X square equals to 3 minus X square plus 1. So we open the brackets on this side of the equation, and we found out that X square equals to 3 minus X square. 3 minus X square equals to 3 square, that is 9, plus X square, minus 2 times 3 times X, that is minus 6X plus 1. Here we have X square on both sides of the equation, so X square will get cancelled. After we cancel X square, on this side of the equation we left with nothing, that is to say 0. In the other side of the equation we have 9 plus 1, that is 10, minus 6X. So in total we found out that 0 equals to 10 minus 6X. Here we added 6X from this equation, and finally found out that 6x equals to 10. Here we divided this equation by 6 and finally found out that x equals to 10 over 6. Here we divided both the numerator and the denominator of this number by 2. 10 over 2 is 5, 6 over 2 is 3. So in total x equals to 5 over 3 units in its length. That is to say, the radius of this circle, x equals to 5 over 3 units in its length. Our mission is to find out the area of this circle. The area of any circle equals to pi times the radius of the circle squared. And again, the area of any circle equals to pi times the radius of the circle squared. So the area of our circle will be equal to pi times the radius of the circle, that is squared. The radius is x. So it is pi x squared. X equals to 5 over 3. Therefore x squared is 5 over 3 squared. So in total, the area of the circle equals to pi times x squared. That is 5 over 3 squared. 5 over 3 squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total, we found out that the area of the circle equals to either 25 pi over 9 square units, so in terms of numbers, the area of the circle equals to 8.727 square units. Okay, thank you very much.